Hey, in this tutorial we're going to be looking at polynomial functions. So there is a fair bit in this video, but hopefully we can get through it okay. So just to recap on what a function is, so it passes a vertical line test. Okay, so remember our vertical line test is if we've got our equation, something like that, then it doesn't matter where we draw a vertical line, we only ever cross the graph once. Okay, if it also passes a horizontal line test, going this way, that's called one-to-one. If it doesn't pass a horizontal line test, like this one wouldn't, okay, then it's called a many-to-one function. The domain is the set of all x values for the function, and the range is the set of all y values for the function. The codomain is a set of numbers from which the range is drawn. It's usually just r. There's not too many times that we have to deal with anything that isn't just r. Now function notation is we usually start off with saying that we've got some function f. The domain might be r, and it goes to our codomain. So that's our domain. This is our codomain. We go comma, and then we actually write our equation. So f of x equals x squared take 3. Okay, then this part's just our function. Okay, so linear functions. Okay, so we need 2 points if we're going to find a linear function. We can't just have one thing. Right? Our 2 points could be like 2 points on a line, or it could be 1 point and the gradient. So by 2 points, you really need like 2 points of information. So it could be 2 points along the line, or it could be 1 point in the gradient. Okay, we call the gradient m, and it's found by m equals y2 minus y1 over x2 minus x1. Okay, where x2 is the more positive point than x1, y1. Okay, so that's the point that's on the right hand side out of the two. Okay, if two lines are parallel, then the gradients have to be the same for the two lines. The two lines are perpendicular, then when we multiply the gradients together we'll get -1, or a different way we often like to use it is saying that the second gradient is equal to -1 divided by the first gradient, m1. Our general form of a linear function is y equals mx plus c. Okay, and we also have this one here that we use. This comes in quite handy, which is y minus y1 equals m outside of x minus x1. So this is the one that we use when we know that we have m, our gradient, and another point, x1, y1. So we find our m and we sub it in for here, and our other points here and here. Okay. If we were needing to find a tangent to a graph, well, this is the one we use. Okay, if we need to find a normal to a graph, okay, then we use y minus y1 equals -1 over m side of x minus x1. Okay, I'm sure we'll come up with tangents and normals a little bit later on. Okay, the midpoint of the line is found by averaging our x coordinates, okay, and averaging our y coordinates, because we'll be given a line segment. Okay, it won't be an equation of a line, it'll be a line segment. Okay, so it's just really averaging our x and our y values. Okay. For quadratic functions, okay, remember our quadratics are the ones that look like this. Okay, it's a parabolic shape. Okay, so it's defined as goes from r to r of f of x equals ax squared plus bx plus c. That's our general form. We say if a is positive or bigger than 0, then it's going to be like a cup. Okay, a is negative or less than 0, it's going to be this way. Okay, c gives us our y-intercept. Okay, b squared minus 4ac is the discriminant, and if the discriminant is positive, okay, then we're going to end up with 2 x-intercepts. If it's equal to 0, we're going to get 1 x-intercept. And if it's less than 0, we're not going to have any intercepts. And we can find our intercepts by using our general quadratic formula, which is this one here, minus b plus or minus the square root of b squared take 4ac over 2a. Okay, remember that's just our coefficients here. Okay, our x-coordinate of the turning point, okay, is found at negative b over 2a, and once we have that we can sub that in to our equation to find out what the other part of our turning point must be. Okay. We actually have a turning point form, which is y equals a outside of x take h squared plus k. H is the horizontal translation, so it moves the graph left and right, and if this is positive, that moves the graph to the left. If this is negative, it moves the graph to the right. Okay, k is the vertical translation. If it's positive, then it's going to move it up. If it's negative, it's going to move it down. And a is what's known as a dilation factor. Okay, so that stretches and compresses our graph. Our cubic functions. Okay, our general form for cubics is f is defined as going from r to r of f of x equals ax cubed plus bx squared plus cx plus d. Okay, in this case, our d would be our y-intercept. Okay, because remember we find our y-intercept by letting x equals 0. So this term, and this term are all going to drop out. Okay, if a is positive, then it's going to be this sort of shape for our cubic. If a is negative, it's going to be this sort of shape. Okay. In our power form, then it's y equals a outside of x take h cubed plus k. So you can see our power form is exactly the same as our turning point form for our quadratic. Okay, we find the same things happen. Okay, if h is positive, we're going to move the graph to the left. If it's negative, we're going to move it to the right. If k is positive, we're going to move it up. If k is negative, we're going to move the graph down. We find that we have a stationary point of inflection at hk. So what our stationary point of inflection means, okay, and I haven't really drawn it very well here, okay, is that our graph has a gradient of 0, okay, at the point hk. So m equals 0, our gradient equals 0 at hk. We have one x-intercept. Okay, in these cases it looks like we're at our origin, okay, but really this could be translated and whatnot. Okay, when we're in this form where we're y equals x take m times x take n times x take p, okay, then we're going to end up with three distinct x-intercepts. Okay, m, n, and p. Okay, we can have a repeated factor, so x take m squared times x take n. When we have a factor that's repeated by squaring it, what it means is the graph comes up, we actually end up having a turning point that is on the x-axis. Okay, and then we've just left with our other intercept. When we go to Kortek functions, okay, they look similar to quadratics. Okay, and again we've got our power form. Okay, so we've got x outside of, sorry, a outside of x take h to the power 4 plus k. Right, again, if a is positive, it's going to look like a cup. If a is negative, it's going to be up the other way. We have our turning point at hk again, and we also have a dilation factor of a. So again, that stretches or compresses. Okay, it's the same with our cubics as well, our last ones, stretches and compresses. Our general form is ax to the 4 plus bx cubed plus cx squared plus dx plus e. Okay, and there's a number of ways that we can have our factor form. So we can have it where we have 4 distinct linear factors. Okay, x take a times x take b times x take c times x take d. That'll mean that we've got 4 x-intercepts at a, b, c and d. We can have a repeated factor where we've got x take a squared times x take b times x take c. So that means here we've got our, again like our previous ones, we have a turning point at our factor x take a. We can have 2 repeating factors, x take a squared and x take b squared. Means that we've got 2 turning points, okay, that are our x-intercepts. Okay, and we can have x take a cubed times x take b. In this case, our repeated factor that's repeated 3 times ends up being a stationary point at a. Right, and we have one other factor b. We can also talk more broadly about higher power functions because we just call this our power form. Okay. When n is even, right, our even power graphs have a parabolic shape. Okay? So they're all that kind of parabolic shape. Now, as our power increases, graphs get flatter at the bottom. Okay, and by that, I mean you can see here our red graph is our y equals x squared. Okay, and our y equals x4 actually goes up steeper. Okay, is actually on the inside of x cubed for most of the time. But when we get very small values of x, our ones that are less than 1, okay, you can see we're actually a lot flatter and we're actually below our quadratic. Okay, and the same thing would happen if we went x to the power 6, would be inside again, but we'd be even flatter down the bottom. Okay, if a is bigger than 0 or positive, again we get that cup shape, okay, or if we're negative it's going to be up the other way. And we have our turning point at hk. And again, a is a dilation factor, so it stretches and compresses our graph. If n is odd, our graphs have our cubic appearance, okay, meaning they're like this. Okay, as the power increases, the graph gets flatter, okay, near the point of inflection, and that's a stationary point of inflection. Okay, so again you can see in our blue is our y equals x cubed, okay, and our red is y equals x to the 5. We're a lot flatter. Okay, if a is positive, we're like this. If a is negative, we're like this. Okay, the way I always think about it is if you're walking across the page this way, okay, if you're walking uphill, you've got a positive gradient. Okay, if we're walking this way, if we have a negative gradient, we're walking downhill. It's exactly the reason why they talk about gradients in cycling. It's just about the steepness of the hill. Okay, and again we have a point of inflection. Sorry, that should be a stationary point of inflection at hk. That's actually a stationary point of inflection at hk. So I want to have a look at a couple of worked examples. Okay, the first one is worked example 2. Okay, we have the line 2x plus 3, rewrite that, 2x plus 3y equals 12. We need to sketch the line and calculate the gradient of the line. Okay, and then we've got one other part which I'll talk about in a minute. Okay, if I was going to sketch this, the first thing I'm always going to do is actually rearrange it and put in our general form anyway. Okay, which is really going to find our gradient of the line in doing so. So we'll do that. We'll make it 3y equals minus 2x plus 12. So y equals minus 2 on 3x plus 4. Okay, and so straight away we can say our gradient is minus 2 on 3. Okay, and our y-intercept, our c, is 4. So we want to graph this. Okay, we're going to be up at 4. Okay, so that means our negative 2/3 means for every 1 across we come down 2/3. Okay, it's a little bit of a pain. Okay, so the easier way to do it is actually find our x-intercept. Okay, and that's when we let y equal 0. So x-intercept, let y equal 0. So we have 0 equals minus 2 on 3x plus 4. So we'll rearrange that and say that, I might do it over here actually, so that we have minus 4 equals negative 2/3 x. So we have minus 12 equals minus 2x. So x equals 6. Maybe up here at 6. Okay, and now we can draw our line. Okay, we should be labelling our axes. Okay, we should really have more of a scale than what I've got on there, and we should also be labelling our equation on here, which was minus 2/3 x plus 4. Okay, and all our graphs really should be done in pencil. It's just you can't really see them very well on the page with the camera if I do things in pencil. Okay, so there's one last part of this question which I think is the part that's far more important. I think a lot of people at this stage doing Year 12 methods can surely draw a linear graph, or it won't take much revision. Okay, the third part though is determine the coordinates of the point on the line that is closest to the origin. Okay, so there's going to be some point on our line. Okay, it's going to be here. I'm going to call it P. Okay, that is closest to the origin. Okay, and if you're cluey, you'll realise that it means it has to be perpendicular to that. Okay, so we're going to let the point P be the point on the line which is closest to the origin. This means that this line here is perpendicular to this line here. Okay, so we know then the gradient of this line, I'm going to start answering this question over here. So the gradient of this line, we'll call that M1, okay, and we know that equals negative 2/3. Okay, and we know that M2, because it's perpendicular, is minus 1 on M1. That was one of our things that we had in our linear section, which means M2 equals negative 1 on negative 2/3, okay, which will equal positive 3 on 2. Okay. We also know, okay, that this red line, okay, also goes through the origin. So we can use our equation y minus y1 equals m outside of x minus x1. Okay, it's quite simple because x1, y1 is 0, 0. So we find that the equation of our line is y equals 3 on 2x, okay, which is handy. Okay, now we haven't actually, because we've got to find the coordinates of this point. Okay, haven't actually done that yet, but what we've done is we've found the equation of our two lines, so now we can solve them simultaneously. So what I'm actually going to do is I'm actually going to go back to this equation, okay, and use it in this form, okay, and say that we've got 2x plus 3y equals 12 and y equals 3 on 2x. I'm going to call that 1 and that 2. We're going to sub 2 into 1, okay, so that we get 2x plus 3 times y. Now y is this though, so it's 3 times 3 on 2x equals 12. Okay, so that means that we get 2x plus 9 on 2x equaling 12. Okay, which means we can say that's 4x on 2 plus 9 on 2x, okay, which equaling 12, which means we can say that we've got 13x on 2 equals 12. Okay, rearranging, I can come up here now. Okay, means that we have 13x equaling 24, and so x equals 24 on 13. Okay, and now we're going to sub x into equation 2, because we've got to find our y coordinate now. This is our x coordinate of our point P. Okay. So this is 24 on 13. It's not a nice number, but you've got to back yourself in. Okay, because maths isn't all about nice numbers, the real world isn't all about nice numbers. Okay, we're not going to get answers that are always nice integers. Okay, so we're going to sub that back in now and say that we get y equals 3 on 2 times 24 on 13. Okay, we can say, well, that's y equals 3 times 12 on 13, which is 36 on 13. Okay, which would be our point up here. That's our 36 on 13. Okay, so all up, our point P is located at our 24 on 13 and 36 on 13. Okay, now I want to do one more work example with you and then we're done. And this one's actually not in the textbook. I just want to do one a little bit differently. Okay, so that's y equals, let's say, minus 2x plus 3, say, squared plus 1. Okay, it's because we've got this number inside, okay, that I really want to talk about this one. Okay, actually, sorry, I haven't done a very good example there. We're going to get not very nice numbers. So let's make it plus 6. Okay, so the reason why I wanted to show you one like this, okay, because if we looked at that and I asked you which way this graph has been translated horizontally, whether it's been to the left or the right, you'd see this positive 6 here and go, okay, it's been moved to the left. But it's actually not the case, it's actually been moved to the right, and it's because of this minus 2 up here. So whenever we have ones where we've got a coefficient of x in here, what you really want to do is take it out as a common factor. Okay, and that way it actually shows us what's happening here. Okay, so we're actually going to be moved to the right for this one. Okay, so our turning point is actually going to be at 3, 1. Okay, and that doesn't really give us a whole heap of information. Okay, so what we really want to do is think about, okay, what would be our y-intercept? Now y-intercept comes when we let x equal 0, which means we do 6 squared, which is 36, plus 1 is 37, so we're going to be way up there, so you can see we're not actually going to be doing a whole lot. And the other thing about this too, if you weren't sure what was going to happen, okay, with this negative here, okay, has actually made it negative this way, and negative actually has to be outside here. Okay, it doesn't actually change whether we're positive like this or like this, and that's basically because this negative is going to be squared, okay, and it's going to disappear. So we're still going to be positive, okay, and we're going to be something like this. Okay, and it's always good, if you're not sure what it's going to look like, just sub in a couple of values of x, see what y values you get. So the point with this one, again, was just to take out that common factor so we could get which way it's been translated correctly. Okay? And hopefully that's enough to get you through the questions on this section.